What if there was a way to turn a differential equation, an equation with derivatives, into a plain algebra problem? That's exactly what the Laplace transform does. In this video, we're going to define the Laplace transform, understand what it actually does, and then walk step by step through the method used to solve a differential equation. Let's start with the definition. The Laplace transform takes a function of time, we'll call it little f of t, and transforms it into a new function of a complex variable that we'll call s. This new function is called capital F of s. To find the Laplace transform of a function, we take that function, multiply it by e to the minus st, and then integrate it from 0 to infinity. The result is the new function, capital F of s. It's assumed that the function that we're taking the transform of is piecewise continuous and doesn't grow faster than an exponential function. Just to recap, the Laplace transform takes a function of time in the time domain and transforms it into a function of s in what we call the s domain. Let's now look at the key idea that helps us understand why we're going to use Laplace transforms to solve a differential equation. The Laplace transform turns derivatives into algebraic expressions in s. This is what makes differential equations easier to solve. A derivative in the time domain, f prime of t, when we take the Laplace transform of it, becomes just multiplication in the s domain, with an initial condition included. Let's look at an example. Here we have a second order ordinary differential equation with an exponential forcing term, and we have initial conditions. When you take the Laplace transform of this equation, you get this algebraic expression in terms of s. The key idea is that derivatives become algebra in s. Let's now look at two examples so that you can see what a Laplace transform actually looks like. I wrote down the definition in this green box, and we are going to use it to find these two Laplace transforms. We're first going to find the Laplace transform of 1. So we have the integral from 0 to infinity. We have e to the minus st. We multiply it by the function 1. That's what we're taking the transform of. And then we integrate with respect to time. We're not going to go through the integration. We'll do that in the next video in this series. For now, we just want to see what the Laplace transform looks like. The Laplace transform of 1 is equal to 1 divided by s. Now let's find the Laplace transform of e to the at. We do the same thing. We integrate from 0 to infinity. We have e to the minus st. We multiply it by our function, which is e to the at. Integrate with respect to time. And this becomes 1 all divided by s minus a. These Laplace transforms are ones that come up quite frequently. Let's now put all of this together and walk through the full process of using the Laplace transform method to solve a differential equation. We start with a differential equation. That's the same one that we had on the last page, and its initial conditions. We then take the Laplace transform. This gives us an algebraic expression in terms of s. And then in step 3, we solve for capital Y of s. The last step in the process is to take the inverse Laplace transform to find the solution, and that solution is y of t. So the inverse Laplace transform takes a function in the s domain and transforms it back to the time domain. We'll go over all of that in another video. And that's it for this video. You now know what the Laplace transform is, how it works, and how to use it to solve a differential equation. In the next video in this series, we'll learn how to compute Laplace transforms from the definition and from a table. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.